Hello? Hello, ladies and gentlemen. I'm sorry about the delay. We can start right away. I'll be presenting grade 11 physical sciences. My name is Musala Liburu, and you can get me on Twitter is @MusalaDL, and on Instagram, my handle is post_silicon. All right, we're going to be looking back at yesterday's homework, and then I will be giving you feedback on the homework. Let's go straight to the homework. Now, you were asked to define power, and then the other question was that a circuit consists of 4 batteries of 4 cells connected in series, each with EMF of 3 volts. The battery is then connected to 2 external resistors of 5 ohm and 2 ohm connected in parallel. That is these 2 resistors here. And then the question was that the 2 resistors are connected in series with the resistor of 2 ohm, which is this one over here. Now, the first question was to calculate the total resistance of the circuit, and then 5 ohm resistor is replaced with a 6 ohm resistor. How will this change influence the following? Right, only increase, decrease, or remain the same? And then 2.2, you are asked, how will the total resistance of the circuit be affected by this replacement of a 5 ohm with a 6 ohm? And also, how will the potential difference over the parallel combination be affected by the change of replacing the 5 ohm resistor with the 6 ohm resistor? And then calculate the cost to run washing machine of 230 volts with a current of 20 ampere for 1 hour if the price of electricity is 85 cents per kilowatt hour. Right, let's go straight away to the solutions. You are asked to define power. So power is the rate at which work is done or the rate at which energy is transferred. Right, and we are asked to calculate the resistance in the circuit. So calculating the resistance in the circuit, we start off by calculating the resistance of parallel resistors. That is the resistance of the resistors that are in parallel. So we start calculating the resistance in parallel connection, in parallel circuit, that is in here first. So there it will be given by 1 over Rp equals to 1 over R1 plus 1 over R2. So R1 is 2 ohms and R2 is 5 ohms. So it will be 1 over 2 plus 1 over 5. Then the lowest common denominator will be 10. So 2 goes how many times into 10? It will go 5 times. And then 5 times 1 is 5. Then we write it here. Then there's a plus here, then we put the plus there. And 5 goes how many times into 10? 2 times. 2 times 1 is 2. So it will be 5 plus 2, which is 7 all over 10. And then this is 1 over Rp. 1 over Rp equals to 7 over 10. Then it means we have to invert if we have to get Rp, that is resistance in parallel. So resistance in parallel will then be the reciprocal, which is Rp will then be 10 over 7. And 10 over 7 is 1,43 ohms. Now, this is the resistance, the total resistance of this parallel connection. So we need to get the total resistance of the circuit. So the total resistance of the circuit will be these ones that are connected in series, in parallel, plus this one that is in series with this two. So total resistance will be R parallel plus 2 ohm resistor. So R parallel is 1,43. The value of magnitude of this one is 2. So it will be 3,43 ohms. That is the total resistance of this circuit. Right, let's carry on. Now, the second question was that a 5 ohm resistor is then replaced with a 6 ohm resistor. How will this change influence the following? Right, only increase, decrease, or remain the same? The total resistance of the circuit, the potential difference over the parallel combination. So in here, we know that now, if we are to calculate the resistance that are in parallel, the resistance in parallel, now it will be, instead of 5 here, we are going to get 6. Then the LCD will be 6. Then 2 goes how many times into 6? 3 times. 3 times 1 is 3. Plus 6 goes how many times into 6 once? And then 1 times 1 is 1. Then we're having 3 plus 1, which is 4 over 6. But this is 1 over RP. We are looking for RP, so we have to invert. Inverting it will be 6 over 4, which is 1,5 ohms. So now the total resistance of the circuit would have increased. So the answer would increase because remember last time it was 1,43. Now it's 1,5. So it means we are adding 1,5 plus 2, which will be 3,5 instead of 3,43 that we get with the 5 ohm resistor. So the answer should be increase. And then for also 2.3, the potential difference over the parallel combination, it will increase. Why? Because V equals to IR. So R would have increased, and then therefore it means the potential difference would increase across the parallel combination. Right. Right. The question was, calculate the cost to run a washing machine of 230 volts with a current of 20 amperes for 1 hour if the price of electricity is 85 cents per kilowatt hour. Now, the cost of electricity will be price multiplied by unit kilowatt. So in here, we need to know how many kilowatts are here. So we need to calculate the power first. So power is VI, V times I, and then which is equals to 230 for volt, take for V, and then 20 for I. Then this will be 4,600. So 4,600 watt is the same as 4,6 kilowatt. Right. So we know the kilowatt now. So the price equals to, the cost equals to price multiplied by the unit kilowatt hour. So the price is 85 cents and the unit kilowatt, it is 4,6. So it's 4,6 multiplied by how many hours is this operating? It is 1 hour. So that the cost will then be 391 cents. So 391 cents is equals to 391 cents. Right. Let's go straight away to today's lesson. Today's lesson is about electromagnetism. Right, at the end of this lesson, you should be able to know the following. One is to the magnet. At the end of this lesson, you should be able to know the magnetic field associated with the current carrying conductors. You should be able to use the right-hand rule to determine the magnitude of the magnetic field be associated with the following: 1, straight current carrying conductor; 2, current carrying loop, that is a singleton; and then a solenoid, that is the conductor with multiple loops or with multiple turns. Right, and then draw the magnetic field pattern around a straight current carrying conductor with singleton, that is a with just loop, and then also across around a solenoid. Right, you should be able to know Faraday's law, state Faraday's law of electromagnetic induction. You should also be able to use the right-hand rule to determine the direction of the current induced in a solenoid when a pole of a bar moves into and out of the solenoid. And then you should be able to solve a problem using the equation magnetic flux equals to magnetic field times area times cos theta, and predict the direction of the induced current in a coil. And then you should be able to solve problem using the equation EMF equals to number of coils over change in magnetic field or magnetic flux over time, over change in magnetic flux over time. That is rate of change in magnetic flux. Right. What is electromagnetism? Electromagnetism, it is the study of properties and the relationship between electric currents and magnets. So we are studying in electromagnetism, we are studying properties of electric currents and magnets, and also the relationship between electric currents and magnets. Right. If you hold a compass next to the current carrying conductor, the needle of the compass will be deflected. Why? Right. It is simply because it will be showing that there is magnetic field around that particular current carrying conductor. And what is electromagnet? An electromagnet, it is a current carrying conductor that has magnetic field around it. So any current carrying conductor that has it will have magnetic field around it. So it will be said to be called an electromagnet. That is, a current carrying conductor will have magnetic field around it while the current is flowing through it. Right. The magnetic field around a conductor are arranged in concentric circles around the straight wire. So that is, if you are having a wire that is carrying current, there will be magnetic field that will be arranged in concentric circles around that straight wire. Right, now how do we then determine, because yes, we can have circles, but how do we then determine the direction of the field? It is determined by using the right-hand rule. And then how does that right-hand rule say? What does it say actually? How it is being used? So the right-hand rule, the magnetic field lines produced by a current carrying wire will be oriented in the same direction as the curl finger of a person's right hand, with the thumb pointing in the direction of the current. So in here, let's look at this diagram. We can see if the current is going up and then you are holding the current carrying conductor, and the current is going up, and your thumb is pointing in the direction of the current, then your curl finger here, will be pointing in the direction of the magnetic field. So this curl finger, you can see this is the magnetic field. So it will be going in these circles because the fingers are pointing this way. So that is what will be happening. So now let's carry on. Right, this is just to deal with a solenoid to get the direction of the magnetic field around the solenoid. Now, let's say this solenoid is coming from this plane of paper and then up and then back into the plane of paper. Now, how do we draw a magnetic field around this solenoid? So if it's coming towards the observer, meaning it is coming towards the observer will be looking from the top of the plane of paper. So this will be a wire. So if it's coming out of the plane of paper, you will represent it with a dot. And if it's entering away from the observer, that is entering the paper, it will be represented by X. Now, if you have a right hand, so in this one it is away, so it means it will then be moving anti-clockwise. But then if it is moving towards, then you will point down with your thumb, and your curl finger will be showing the direction of the magnetic field. Right, now what happens if you are having a solenoid? So in case of a solenoid, if you hold a solenoid with your right hand, your curl finger will point in the direction of the current, and then your thumb will point in the direction of the magnetic field. That is the north of the magnetic field. So if you look at this one, if your curl finger is pointing the direction of the current, your right hand curl finger is pointing in the direction of the current, then your thumb will be pointing in the direction of the magnetic field. That is in the direction of north. Right. And then what you need to remember is that some materials will behave differently around the magnetic field. So some of the material can easily be magnetized, whereas others are difficult to magnetize. And then some of this material will lose magnetism easily, while others will be difficult to do so, will not lose magnetism easily. So soft magnetic materials are said to be materials that can easily be magnetized and be demagnetized easily. For instance, iron. And then hard magnetic materials are materials that are difficult to magnetize and retain magnetism for a longer period of time. For instance, steel. I hope we all know a difference between steel and iron. So because iron is a pure metal iron, element iron, and then steel is a combination of iron, chromium, and a certain percentage of carbon. Right, let's look at factors that determines the strength of electromagnets. Then here are articles of magnetic and video recorders, telephone receivers, relay, and also electric bells, and also lifting magnets. So these are some of the uses of magnets. Right, let's look at Faraday's law of electromagnetic induction. So this law states that the magnitude of induced EMF across the ends of a conductor will be directly proportional to the rate of change in magnetic flux linkage with the conductor. So the magnitude of the EMF, induced EMF across the ends of a conductor, is directly proportional to the rate of change in magnetic flux linkage with the conductor. So in here we say epsilon, which is representing EMF, equals to minus n. So in here, n is representing the number of turns in a coil, and then change in phi, it means it is change in magnetic flux. So phi is representing magnetic flux. So change in phi is change in magnetic flux, and then delta t is change in time. Right. So note that delta phi over delta t is the same as the rate in change in magnetic flux. Right, so we have said the induced EMF is directly proportional to the rate of change in magnetic flux across the end. So it is directly also proportional to the number of turns in a coil. So now, magnetic flux will be calculated using the symbol using this particular formula here to say magnetic flux equals to magnetic field multiplied by the area and then the cos of theta. So phi is magnetic flux, and the unit for magnetic flux is Weber, and one Weber equals to 1 Tesla meter squared. So B, it is representing the magnetic field strength, and it has a unit, Tesla, which is capital T. And then A is the area that the loop occupies. And then theta is the angle between the magnetic field and the line drawn perpendicular to the face of the loop. So if you are having the loop here, theta, the angle theta will be the angle between the magnetic field and the line drawn perpendicular to the face of the loop. So that's basically what every aspect means. Every one of the variable means in this equation. Now, we want to determine the direction of the induced EMF, the direction of the flow of induced current, because EMF will be, if EMF is induced, there will be flow of current. So we try to apply Lenz's law. So Lenz's law says the direction of the induced EMF drives the current around a wire will always to always oppose the change in the magnetic field flux that causes the EMF. So the direction of the EMF drives the current around the wire to always oppose the change in the magnetic flux that causes the EMF. So what is happening is that always the induced EMF will drive the current in such a way that it will oppose the change that causes a magnetic flux. That is the change in magnetic flux that causes the EMF. Right. So what does that mean? Let's look here. If the north pole of the magnet approaches the coil, like we are seeing here, the north pole is induced in the coil to oppose the approaching magnet. That's what it means. So, meaning that the induced EMF will always oppose the change in magnetic flux that causes the EMF. Now, if the magnet is being removed from the coil, what will happen is that you will have this, this will be the north pole going away. So if it's going away, now the coil will induce induce the south pole here, so that it attracts the magnet. If the magnet is being moved out, the induced EMF will try to oppose this by inducing the south pole, which will try to attract this particular magnet back. Here, if the magnet is being sent with the north pole, the induced EMF will induce the north pole to oppose the magnet going into this coil. So if the magnet is being pulled out, the induced EMF will try to induce the south pole to attract it back. So it is always opposing the change in magnetic flux that causes it. Right. Let's try to apply the right-hand rule to determine the direction of the induced EMF in the coil. Now, if the thumb points away from the magnetic, from the bar of the magnet, that is the bar magnet, then the curl finger wrapped in clockwise fashion, which is the direction of the induced current. So the right-hand rule here, it is used to determine the direction of the induced current in the coil. Now, how do we know the direction? So if we are having the coil here, and then the magnet is coming in and out, how do we determine the direction of the current? Now, how do you do it is that, remember, previously we were having, in case of the current carrying conductor, your thumb was, in case of a solenoid, your thumb was pointing in the direction of the magnetic field. But here the thumb is pointing opposite to it is pointing away. Your thumb is pointing away. So if your thumb is pointing away, it means it's pointing to the south of the coil. So if it's pointing away, it means the curl finger will be showing the direction. So it means if your thumb is pointing away, it will be pointing this way. Then your curl finger will be showing the direction of the magnetic field. Sorry, not magnetic field, but the induced current. So if your thumb is pointing away from the magnetic field of the bar, your curl finger will be pointing in the direction of it will be pointing in the direction of the magnetic field. And then now, in here, the south, it is where your thumb will be pointing. So if your thumb is pointing south, remember, you must always, in here, in order to predict the direction of the induced current, you must point away from you must be pointing away from the direction of the magnetic field. So pointing away would mean pointing to the south. So if your right thumb is pointing towards the south, which is this one, it means your curl finger will be showing you the direction of the magnetic field. So in this instance, it will be clockwise. And in the previous one, it was going anti-clockwise. Right. Now let's carry on. I'm going to try and see if we can do this example and see how far we can go. The arrangement of the apparatus to demonstrate Faraday's law of magnetic induction is shown below. State 1.1 state Faraday's law of magnetic induction in weights. And then state 2 ways in which the deflection of a galvanometer can be increased. Right. And then a coil with an area of 0.6 square meters is held with its axis coinciding with the direction of the magnetic field of strength of 0.4. And then calculate the magnetic flux linkage. And then in order to produce 9 volts, the area of the coil with its axis coinciding with the direction of the magnetic field is half from 0.6 meters square to 0.3 meters square in 2 minutes. Calculate the number of turns in a coil. So the first thing, let's just straight away go to this. State Faraday's law of electromagnetic induction in weights. So it says that Faraday's law of electromagnetic induction in weights, it says the magnitude of the induced EMF across the ends of the conductor is directly proportional to the rate of change in magnetic flux linkage with the conductor. So the magnitude of the induced EMF across the ends of the conductor is directly proportional to the rate of change in magnetic flux linkage with the conductor. And 2 ways of increasing the deflection of the galvanometer, it will be to increase the speed at which the magnet and the coil move relative to each other. So if you move the magnet in and out quicker, in and out of the coil quicker, the induced EMF the galvanometer will deflect more. That is, the induced EMF will increase. If you increase the strength of the magnet, it will also increase. And if you also increase the number of turns, it will also increase. Right. The second question was calculate a coil of a coil with an area of 0.6 square meters is held with its axis coinciding with the direction of the magnetic field of strength of 0.4 Tesla. Calculated magnetic flux linkage. So magnetic flux linkage equals to what? Equals to BA times cos theta. So what is BA here? B is magnetic field strength, which is 0.4 Tesla, and then the area is 0.6 multiplied by the cos of theta. So cos of theta will be 0 because it is coinciding with the direction of the magnetic field. So that will give you 0.24 Weber. So the next question was to calculate, in order to produce an EMF of 9 volts, the area of the coil with its axis coinciding with the direction of the magnetic field is half from 0.6 square meters to 0.3 square meters in 2 minutes. Calculate the number of turns of the coil. So we know that this is EMF is given by a number of coils multiplied by change in magnetic flux over delta T. So EMF will be a change in magnetic flux here will be change in PA. So because here, change in area here. So changing, the area has changed from 0,3 to 0,6 to 0,3. So this difference will give you 0,3. So that is why we have said this will remain the same. The magnetic field strength will remain the same. But what is changing? It is this the area. But the area is changing from 0,6 to 0,3. So that difference is 0,3. So now if you calculate, you should be getting your answer to be let's see, number of coils here is what we are looking for. So we have substituted P, which is 0,4, and the change in the area is 0,3 there, which will, all of this will then represent the change in magnetic flux. And then you should be getting your answer to be 9,000 tenths. Right. All right, this will be your homework for today. All right, let me read question 3. Question 3 should read, the coil rotates through an angle, The coil rotates through an angle of theta to a position where the magnetic flux becomes 0. And then you have to calculate the magnitude of theta. Calculate the magnitude of theta. So let's just close on. I think you have learned something from this session, and then let's meet tomorrow. Tomorrow we'll be looking at this homework and types of chemical reactions. And then you can always get me, contact me on musala.liguru@gmail.com, or on Twitter is @musalatl, or Instagram is pulse_silicon. So until then, bye-bye.